So this week you'll have to be making solutions and dilutions, and there are lots of units associated with that. So we're just going to walk up through how to make solutions, what a solution is. A solution is a liquid homogeneous mixture with two or more components. The component that is in the majority is called the solvent, and the component that is in the minority is called the solute. So you can have multiple solutes. You can dissolve lots of different things into the same solution or the same solvent. In this case, in this 2 weeks, you'll be thinking about water as your solvent and perhaps a dye and a sugar in a drink that you're going to be investigating. So both the dye and the sugar would be called solutes, and they are in smaller amounts than the water. We characterize solutions by their concentration. So we can talk about dilute solutions and concentrated solutions. Dilute solutions have only very small amounts of particles or solutes in the solution. So for example, here's a bunch of, maybe this is a dye, but maybe this is juice, right? Where you've watered down your juice and you have very few actual juice molecules and most of it is just water. And you have more and more of your solute particles until a concentrated solution has a lot of solute particles. We can quantify this concentration in many different units depending on what we're looking for, what experiment we're doing. But it comes down to basically two different forms of concentration. Either it's classified by the amount of solute divided by the amount of solution, or the amount of solute divided by the amount of solvent. And sometimes these two will give you very similar answers, but it really depends on the application in which you're looking at in lab or in class. The most common units of concentration that you'll be looking at is molarity. So the capital M, molarity, has moles of solute divided by the liters of the solution, so the total volume of the solution, which is solvent plus solute, okay? The mass percent that you may see, this is easily from food labels and that sort of thing. Mass percent would be given as the mass of solute over the mass of solution times 100% just to get it into percent. And the mass of solution here is the mass of the solute plus the mass of the solvent, but it's just the total mass of your solution. Molality is a lowercase m, and that is the moles of the solute, just like molarity, but now divided by the mass of the solvent rather than the solution. And so here we're in this version where we're doing solute over solvent rather than solute over solution. And then mole fraction is moles of solute over total moles of solution. So moles of solute plus moles of solvent. So molarity, mass percent, and mole fraction all have solution values in their denominator. So we're looking at this first representation. Molality has moles of solute per mass of solvent or amount of solvent, and so that's the only one in this second representation. We use molality and mole fraction a lot when we get to colligative properties of solutions later this semester, but in lab we generally use a molarity or a mass percent. So how do we make a solution? If we're thinking about concentration units in molarity, we have the moles of the solute over the liters of the total solution. So here I have a beaker and I've put some solid solute in there. Maybe this is cobalt nitrate and I have 1.47 grams of cobalt nitrate. I can use the molar mass of cobalt nitrate in order to determine the moles of cobalt nitrate that are there, and I need that for the moles here in my molarity. And then I'll fill this up with water to the volume that I need. I need 150 milliliters of solution. I want to make sure that I have that in liters units because molarity is moles per liter, not moles per milliliter. And then I mix that up and it becomes a solution. All of my cobalt nitrate will dissolve and make a homogeneous mixture, and my molarity now, capital M, will be the moles of solute that I found from my mass of cobalt nitrate divided by the liters of solution, my total volume of my solution now. So this would give us an answer of 5.36 times 10 to the minus 2 moles per liter, or molarity. If you want to make 50 milliliters of a 0.17 molar solution of sugar water, how much solid sugar should you dissolve into 50 milliliters of water? So you can pause the video here and try this problem on your own before we walk through it. All right, the molar mass of sugar, or sucrose, is given here. And so we need to convert our mass, or we were looking for a mass. How much solid sugar should we use? We know what the concentration is that we want, and we know the volume that we want. So we have two of the three variables in this equation. We know the concentration and we know the volume. So we're going to put those numbers into our equation, rearrange by multiplying both sides by liters, and solve for moles. Once we have moles, we can then multiply by the molar mass of sucrose in grams per mole, so that our moles will cancel and we'll get grams. So molarity times volume, again, has to be in liters to make sure your units cancel, will give you moles. So, and then moles divided times the molar mass will give you grams. So here's our molarity, here's our volume in liters, will give us moles, and then we use the molar mass to get to grams. So in order to make this solution that we want 0.17 molar solution and 50 milliliters of it. I'm going to weigh out 2.9 grams of sugar and dissolve that into water. Now, the act of physically making a solution or preparing a solution, you should weigh out the solid that you need and use the appropriate glassware. Maybe that's a volumetric flask. And you should always put some water into the flask to begin with. So make sure there's some solvent in the flask so that when you add the solid, you're adding it to a liquid. You're not adding the liquid to the solid, but you're adding the solid to the liquid. Add the solid compound and then swirl it around a little bit to get it started dissolving. After it's dissolved, fill the flask to the line with the solvent. Maybe you're using an eyedropper, or maybe you're using one of these water bottles, so you can just drip drop to get that meniscus right up to that line, to be as precise as you can. And then mix the entire solution well, either with a stir bar, which would go in the bottom and spin around and mix up your solution. We don't usually use those in our general chemistry labs, or by inversion. And so inversion means that you're going to cap the flask in some way, either with parafilm or with a stopper or your thumb, and you're going to turn it upside down. And this air that's in the neck is going to make a bubble. At the top, you're going to turn this upside down, and it's going to make a bubble at the top, and then you invert it right side up, and then you want to wait for the air bubble to get all the way up to the top here, and then turn it upside down again, and you do that maybe 12 or 13 times, and you've got a pretty good mix, as long as it's all dissolved. To make a dilution, you can also make a solution from a concentrated solution. The concentrated solution would be called a stock solution. And so here I have a beaker of 6 molar hydrochloric acid. It is a very concentrated solution, and we'll call that our stock solution. But what we want to use in the lab is of a lower concentration. So I'm going to have to take a little bit of this and put it into a larger volume in order to dilute that to a lower concentration. The equation that we use to predict this is molarity of your initial solution times the volume of your initial solution is going to equal the molarity of your final solution times the volume of your final solution. And you'll hear this, the TAs or the instructors will often call this M1V1 equals M2V2, and you'll use this a lot in lab. And the idea here is I'm going to take a known volume, volume of my initial solution. How much am I going to use to do the dilution? In this case, 1 milliliter. And I'm going to transfer that into a different solution, to dilute it. So I know the concentration of my initial solution. I know the volume of my initial solution that I'm going to use. And then I'm going to fill this up to whatever volume I desire, so 150 milliliters. I'm going to mix it well, okay? And then I can do my calculation. What is the concentration of my final solution? Again, your initial solution, your stock solution, the two values for your stock solution go together, 6 molar and 0.001 liters, okay, because I used 1 milliliter. I'm going to solve for the concentration in my final solution, and I have made 0.15 liters of that, 150 milliliters. So I can rearrange this equation by dividing both sides by 0.15 and solving for the final concentration, and that will give me 0.04 molar. So here's another practice problem. If you want to make 50 milliliters of a 0.05 molar solution of sugar water, how much of the 0.17 molar solution should you use to mix into a total of 50 milliliters? So your final volume should be 50 milliliters. Your final concentration, right, is 0.05 molar, and your initial concentration is 0.17 molar. So the question is, how much of that stock solution should I use in order to make my final solution, which is a 0.05 molar solution, and I want 50 milliliters of that. So I'm going to set up my M1V1 equals M2V2. Again, the question is, what is the volume of my stock solution that I need? I'm going to rearrange this by dividing both sides by 0.17 molar and solve for my volume. So I would transfer 14.7 milliliters of the stock sugar solution into a 50 milliliter volumetric flask and then fill it up with water to the 50 milliliter line, and that would give me 50 milliliters of a 0.050 molar solution of sugar.